Yeah, so I changed the title a little because David can't be here, so I will give his talk basically, and only parts of what I wanted to say. So let me first recall what FDC was. I think all of you were here on Monday, but let me quickly define it again. So we say a metric family, and it just means a family of metric spaces, decomposes over class C if for every R there exists the decomposition of xi into two subspaces ui0, ui1, and further decomposition, which is now R disjoint, into subspaces Vij epsilon. So that's the family of all these subspaces is contained in C. And now let D be the smallest class that is closed under decomposition. And contains all uniformly bounded. And this is yet another definition of FDC, so it's equivalent to the ones we heard on Monday, but it's shorter, yes. Uniformly bounded just means that there exists a bound on the diameter, so supremum. So, well, yeah, it may be bounded. It depends on who you ask. So it just means, so use the diameter is bounded, so it's supremum. I mean, if the supremum is smaller, infinite, then it's smaller than a fixed number. Okay, and this one is equivalent to the game definition and also to the one with the ordinals. Yes. Yeah. Yes. And so we will need some notions from course geometry. So let me quickly do some definitions. So a map between families is a set of maps between elements of the families, such that for every x there's some y and some map that has x as a domain. Yes. And also several x can map to the same y. But every x has to be in the domain of one of the maps. And it is coarse if there exists some function rho such that for all, and also all x first, 2 points, we have that the distance between the images is bounded by rho of the distance of the points we took. So points that are relatively close together will stay relatively close together. Yes. and it's a coarse embedding. If it is coarse, and there exists also a delta, and this one should be a proper map, such that we also have this inequality from the other side. So this will tell you that points that are far apart will stay far apart, and we just need proper here so that this function really goes to infinity and not just is a zero function or something. For rho it doesn't matter actually. I mean it's stronger if it doesn't. No. And now, so the reason that we can actually talk about FDC for groups is, well, first thing, it's a coarse invariant. So if you have a coarse embedding and Y has FDC, then also X has FDC. And now we have the following proposition. Every group, and groups will always be countable and discrete. And there exists a proper left invariant metric on the group. And every two are coarsely equivalent. That basically needs you have a coarse embedding in the other direction and both are close to the identity. But actually for this is the identity on the group with the two metrics will be a coarse embedding. So we can say a group has FDC if and only if it has for some and then all proper left invariant metrics. And now the theorem that was already mentioned by Romain from then Romain and Gouliang. G has FDC and the finite model for EG, then the assembly map split injective, and let me tell you a little bit about the proof, but just a very rough idea. So the first one is that this one is a colimit over the Rips complexes. So the Rips complex is a simplicial complex with the vertices G and some G1 to Gn span a simplex if the distance is pairwise less than S. So this somehow brings the geometry into game. And here, well, if you would have arbitrary groups, then this here would be a e.g. underbar, but if it has a finite model, then it's torsion free. So, and now FDC implies that so we can do a Meyer-Vittorus argument to show that the unequivariant assembly map is isomorphism. And so, well, I won't really say what the unequivariant version is, but this one is like fixed points of two of spectra, and you can also do that without taking G fixed points. And then the next step is you compare the fixed points with homotopy fixed points. It's just equivariant maps from EG to X. And this will allow you to get the property back to the equivariant assembly map, but it will only, this comparison map will be an isomorphism on this side, but not on this, and that's why we only get split injectivity. And here's also where the finite model assumption comes in, because for one of the maps to be an isomorphism, we actually need to take the homotopy fixed points outside of the co-limit, and for the other one, we need to take first the co-limit and then the homotopy fixed points. And well, this is a homotopy limit, so we can only commute it with a co-limit if we have a finite model, because then this one is a finite homotopy limit. And so what I did in my thesis was some generalizations of this theorem. So let me just add the differences here. So to show that the equivalent assembly map is an ISO, it's only true if you take the co-limit. It's not true on the individual steps. But that the comparison map down is an ISO that only holds for co-compact subsets, so only for the individual steps. So this one, yes. This one's only an ISO if you take the co-limit outside on this side. Okay, so the first generalization we can do is we allow for torsion. And then for this comparison map here to still be an isomorphism, here we have to what I call proper homotopy fixed point, so having all equivariant maps from E underbar G to X, but then it doesn't suffice anymore that X has FTC. We needed some equivariant version for the finite subgroups. And this is equivalent to asking that for some or all finite subgroups, this quotient has FTC. And now you can do another generalization. You can, instead of finite, you can add finite-dimensional. And so in this case, this is no longer a finite homotopy limit. But what you can do is you somehow prove this isomorphism on the whole skeleton at once. So in the whole zero skeleton, and then you only do a finite homotopy limit over the skeleton, and then it still commutes. But to do it for the whole zero skeleton at once, all the quotients will appear there. So it doesn't suffice if they all have FTC individually, but we really need that the whole family, and it should also be in blue, has FTC. No. So in my the first paper, there's an extra condition on the bound, but that can be removed. It actually is easier if you do the other proof without the bound. So we got two corollaries from this. If G is a subgroup of and say first a discrete virtually connected Lie group, then the assembly map is split injective. And here, well, we already know that G has FTC if it's a subgroup of a virtually connected Lie group, and you can actually show that it still holds true if you have all this family here. And this discrete is just there to assure that we have a finite dimensional model for the classifying space I don't know, but I think there are some. And actually, so you don't need discrete here. You could also just ask for a finite model for the classifying space and then have some subgroup that doesn't need to be discrete. So for that one, I'm not sure. But I have another corollary with other groups, and those we don't get for the whole Farrell-Jones. So the other example is linear groups. Well, you take G with a discrete metric. You don't take it with a sub-metric. Yes? Okay. Really? I'm not sure how we prove that. I would. But that's not but it doesn't have a free action of the group if the group isn't discrete. So if it's a discrete subgroup, you get the condition of the finite-dimensional model for the classifying space automatically. If you don't assume discrete, you have to assume this. And I don't think it follows. So the second is if G is a linear group, and linear here means subgroup of GL and R, where R is some commutative ring with unit. No, commutative ring with unit. And you need a finite dimensional model. Then alpha is split injective. And to prove first, you prove it for fields, and then you can also prove it for domains because I'm bad into product of fields. And for arbitrary commutative rings, you first have to divide out the nil radical, and there's just a nilpotent subgroup in there. And for example, if you have GN of a field of positive characteristic, I think this always holds. It's a finite dimensional model, so this gives lots of examples. And also this condition can actually be rephrased in terms of the group. So this holds only if there's an upper bound on the rank of the abelian subgroups. So some of the weakest thing you can imagine. So we see we get some groups out of this theorem, but it's still this condition about the quotient. It's not very nice. It's really hard to check it in, case by case, and there's some lemma. So if G has finite asymptotic dimension and we have some finite subgroup, then it follows that the quotient still has finite asymptotic dimension. So maybe I'll define finite asymptotic dimension again. Yes. So I don't have an example of a linear group that doesn't have finite asymptotic dimension and a finite model for the classifying space. But I don't know. I mean, I think it's not known if they're all. Yeah. So, I mean, for linear groups, you can have like some infinite direct sum of copies of Z in there, and then it won't have finite asymptotic dimension, but it also won't have this finite dimensional classifying space. But to prove it somehow, you can only prove FDC really, and then assume this, and I wouldn't know any other way. So for of a positive characteristic, you actually have finite asymptotic dimension, and not in the other case. Let's say asymptotic dimension of X is the smallest n such that for all R there exists an n-dimensional bounded cover U of X with the back number R. So this means that so bounded means that supremum of the diameters of the U's is bounded. N-dimensional means every point sits in most n plus 1 of the elements of the cover, and the back number R means every R ball sits in one of the elements of the cover. And now the proof of this lemma is really easy. You just take the cover you have for G and you push it down to the quotient. And then the dimension might increase, but it will still have the same Lebesgue number and still be bounded. So actually we have that they have the same asymptotic dimension, but that's harder to show. So now from this, so that two questions. First one is, if the asymptotic dimension of G is finite, does this imply that this family has finite asymptotic dimension? And so this is if there's no upper bound on the order of the finite subgroup. Otherwise, this proofs will just work for all of them because it only increases the dimension. And so this was my motivation for showing that this is actually the same, because this would be somehow the first idea if you want to get a counterexample. You would try to find something where the dimension rises with the order of the group and then try to use that. But yes, with the order, yeah. But so actually it doesn't. But the first idea would just give you this, and it's then harder to actually get that one. So second one is, what about FDC? So with that I mean, if G has finite decomposition complexity and you have a finite group, what about the quotient? And this was somehow our motivation to study this notion of regular FDC. But so we still don't know. Still. Which one? Because a family has finite asymptotic dimension is not the same as each space has the same, but the diameter bounds that appear have to be uniform about all elements in the family. So if so the uniform bound has to be uniform over the whole family. And this might fail in this case. So, I mean, no, I mean, you can have a family where every element has asymptotic dimension 1, namely you take n, and so dn is the n ball in Rn, and you blow it up by n. This one has, I mean, it's bounded, so it has asymptotic dimension 0. But if you take this over all the n, then the asymptotic dimension is infinite. So now we have regular FTC. And this is joined with Andy Nikas and David Rosenthal. And the definition is pretty similar to that of FTC. So we say X regularly decomposes over C if there exists a coarse map from X to Y such that Y has finite asymptotic dimension and some of the pre-images of all balls, so for every R, it's a family where this is, so F is an F and Y is in some Y. License C. So these are some of the coarse fibers. So if you have your, say, this is my space X, then mapping down to Y, then in here I look at all the balls and then their pre-images in X. And now we can do the same definition with this notion of decomposing as for FTC. So we so having that one is harder than having FTC. Yes. And I'm going to say why in a minute. So let R be the smallest class closed under regular decomposition, containing all bounded families. And then we say X has regular FTC if and only if it lies in R. So there is the theorem that if the asymptotic dimension of X, or maybe no, let's say Y, smaller than, so it's finite, then it has FTC. And so this space has FTC. And now assume C was a class of spaces with finite decomposition complexity. Then also by the fibering theorem X has FTC. So we have this, it's called a proposition. R is contained in D, and the proof is fibering. Yes. So for FTC, this is actually a theorem, and for regular FTC, that's obviously true, because you can just take the identity here, and then the pre-image is bounded, because it's just this set again. And so it follows that it has regular FTC. But for FTC, you have to do something, because you can in FTC you're only always allowed to decompose into two subsets. But for asymptotic dimension, you can do it into n. And the point, so the idea is that, so here the, well, say that again, two. Yeah, so this is in the following, which is also proof of the theorem. So the proof is you have a space of finite asymptotic dimension embeds into a product of trees. And, or actually it's Gromov zero hyperbolic spaces, but let's think of trees. And now what you can do is you can decompose, well, each tree has asymptotic dimension 1. So you can find the decomposition into two sets, and then you just pull it back along F to get the decomposition of X into two sets, and then you do it for every of these vectors. And so after n steps, you are actually have a usual decomposition of X and end up with something in C. Okay. No. So this is called regular because the point is that if you have FDC and you have your decomposition, then for every R, they might look like completely different. So even if you just look at the case R2 and say for the first R, well, we take this decomposition we have already seen. But now for the next R, maybe I just take that one. And then for the third, maybe just another direction. So they don't have anything to do with each other. I mean, in this case, it still looks all the same, but just imagine something complicated. And now, here, if you have, say, y has asymptote dimension 1, then if you take bigger and bigger r's, it will all look the same. So somehow it's like fibering, of, like in this picture. If I take now bigger intervals, then it will look the same, roughly. So it's contained in one another. And this doesn't, and for FDC, it might just like look completely random. No, well, yes. So this theorem is complicated, but that was known. I mean, that was true. So the case if Y is a proper metric space, that was done by Donishnikov, I think, and then Günther, Teixeira, and you showed that by some ultra limit argument, it actually holds for all metric spaces. So it's not easy, but that was known, and this somehow implies why this implies FDC. And yes, yeah, and then it's just an application of fibering. And so, in case you forgot what fibering was, let me just remind you again. It is basically this definition where Y also lies in C. Well, it actually is this definition where Y also lies in C. Yep. That we will hopefully see at the end of the talk. Because it has one more permanence property. And that will be the last one I will tell you. So C is closed under fibering if, well, we are in the same situation as above. We have some coarse map, Y is in C, and, well, this family of the pre-image of all the R balls is in C for all R, implies X is in C. And so the first theorem we proved is R is closed under fibering. So the idea is the same as proving it for FDC. If you can also interpret this definition as a game one or one with the ordinals. And so you first decompose your Y, regularly decompose your Y, and then in the next step you regularly decompose your fibers. And that's like the same proof as for FDC that this works. And this has a nice corollary. No, it also holds for FTC. And this is the reason why this one implies FTC basically, because this is just a special case of fibering where we assume that the base has a finite asymptotic dimension instead of lying in C. And this also is why we get this following corollary. R is the smallest class closed under fibering that contains all families with finite asymptotic dimension. Because, as I said, this one is just a special case of fibering. And if we assume that Y, so if this family with asymptotic dimension already is in my class. This gives another definition, which I think is a nice definition, because this is somehow how I would think of FTC maybe. You have like all the spaces with asymptotic dimension, and you can close it under fibering. And now, there are actually more permanence properties you want to have. And so, this is not a real theorem, but I will explain it. If C is closed under fibering and contains all families with finite asymptotic dimension, then it has all other permanence properties. Of course, all is not well defined. And with all I mean the ones we know for FTC. Union, finite union, limit, cause invariant, and I will say something more about these in a minute. And so the nice thing here is I just took any class that satisfies these things. So this theorem actually implies, so reproves all the permanence properties for FTC once you have shown fibering, and also for all the other notions. So they are like straight FTC and I don't know, probably, so these things are, if they're closed under fibering, then it shows all the other permanence properties for these as well. So this is also strong. So let me start proving some of these things. So 0 would be cause invariance, and cause invariance means if this is the cause embedding and Y is in C, then X is in C. Well, and this is just a special case of fibering, because now, we assumed Y is in C, and cause embedding will tell me that this class is still bounded. So this one's obvious. And I should say for regular FTC, we actually had to prove it first by hand to get that it's closed under fibering. But, I mean, this one you would want to have for all things you would call a cause property of spaces, otherwise it doesn't really make sense. No, the next one would be finite union. So this says if, and now let me just go to spaces instead of families, because otherwise the families is just another index I have to carry around all the time. X is a union of 2 such that they are in C, then X is in C. So I guess I can fit the proof here. We define F from X to non-negative reals by just defining F of some X is the distance of X to X1. This is a cause map, and if you look at the fibers, then BR of some point T in R is contained either in the interval 0 to, I don't know, say 3R, or from 0 to infinity. And so the pre-image is either contained in the 3R neighborhood of x1, which is in C by cause invariance, or it is contained in x2. Because if this is not 0, then x wasn't in x1, so it was in x2. No, I mean, it's all cause properties, so all the metric cares, it's not about being closed or anything like that. And so the last one I want to mention is union permanence, because we already had that on Monday. This says if X is a union of some xi, and for every r you have some yr, such that the distance of xi without xj is bigger than r, and the family of the xi's and the yrs are in C, then x is in C. And now we can basically do the same trick again. We now define f from x to, and this will be I cross, well, let's say n, modulo I cross 0, so like a tree with one vertex with infinite valency and then the other one, and then just lines. So this has asymptotic dimension 1. And we map, so say we first assume that we have a sequence y1, y2, including in y3. So we can just do that by taking the unions, because we already know union permanence. And then f of some x in xi is I comma the smallest n with x and yn. And now again we have the property that if you pull back, so every point in is contained in either I cross n bigger than 0, so the pre-image lies just in xi, or in I cross 0 to 3r, and this is then just, so f, so the pre-image is either contained in xi or in y3r. And both were in C. So again, from fibering we get this property. And having all these permanence properties will actually also imply a lot of things for groups. So I mean, that's what we basically really care for. I guess most of you at least, that you don't interested in general metric spaces, but in properties of groups. So let me just tell you the list of things this imply for groups. The class of groups in C is closed under the following. Extensions, direct unions. So this would use limit permanence, which I didn't do. Free products. With amalgam. And relative hyperbolicity. And it contains linear groups, so all linear groups and all elementary immutable ones and all discrete, so countable subgroups of virtually connected Lie groups. So the same list that we had for FDC. And now this somehow shows that this will hold for all the notions you can build that are similar in the sense that they are still satisfy fibering and include finite asymptotic dimension. And so now comes a property that we have for regular FDC that we don't have for FDC. Yes, yes. And it also holds for L theory. L theory and also for A theory that will also work. Okay, so X has regular FDC, and so we have a isometric action of a finite group. And the quotient still has regular FDC. And this was strangely hard to prove. The basic idea is the following, that if you have your map from X to Y, not equivariant, but then you can just build an equivariant one from X to F product of Y, that still has finite asymptotic dimension. And now we can have a map from F mod X to this. This still has finite asymptotic dimension because for asymptotic dimension taking this quotient was okay. And now we would want to do an induction about the situation. So now someone would like to say for the fibers of this map, they have like complexity 1 lower. And so we can do an induction of, so then transfinite induction over these ordinals. The problem in here is that the fiber of this thing is actually like F times some old fiber mod F. So where B is F, the inverse union of some R ball. And now this one has like complexity 1 smaller, but now we had to apply a finite union to say that this one still has regular FDC. And if we want to do this induction, but that increased our ordinal by 1. So we go in a circle. And to avoid that, we actually had to prove that under finite unions, the ordinal stays the same. So if you do this ordinal definition of regular FDC. And this wasn't so easy because, so what's the situation? We have x1 to some y1, x2 to some y2, and now we somehow want to get a map from x1 union x2 to, well, if those two lie in like one big space, you could say like something like y1 union y2, but I mean just some two arbitrary spaces. So how do you extend your map from x2 to y1, say? And this is hard. I mean, you can say something like, oh, it just takes the closest point, but then you won't get a coarse map. And so what we had to do is build some kind of cone on y1 where we cross it with a half-open interval and scale the metric when going to infinity and show that this still has finite asymptotic dimension. And then you take the product of the two cones and you get this map. And it still has the same fibers. And the corollary is, yes. Yeah, so here it's it's really using like regular decomposition and not fibering about two things. So it's well then, I mean here you have it's not a disjoint union, so it wouldn't. I mean this is just X is some union of two things. It's not the disjoint union of the two things, and so there might be an intersection where you don't know what to do. And also they're not infinitely far apart, so you can't just snap them infinitely far apart if you want a coarse map. So if G has regular FDC, a finite dimensional model, and upper bound on the order of the finite subgroups, then the assembly map, we write down once more. The split injective, which we just got from the fact that if we have an upper bound, so this works then in families here, so we get that this quotient has regular FDC, so it has FDC, so we get injectivity. So this is like a weaker theorem. Yes, so this is really just a weaker theorem, but it is much easier to prove actually, because now having this notion of regular FDC, because now we just need to prove something about the group. Yes, that's true. So if you just assume we have an upper bound for the groups that we are interested in, and now proving that it has regular FDC, we have all the tools you need, like extensions and free product, direct unions, relative hyperbolicity, and even extensions. Say we know for some groups that this quotient by the finite subgroups has FDC, and now you put it into extension. And the big group suddenly has a lot more finite groups. So you have to take a lot more quotients, but you didn't say anything about them. So you really need to prove something about like all quotients by any finite groups that somehow acts on it, or actually even acts on some kind of union of these things, would still have FDC, and that's yeah. And so, for example, I proved that this property with the finite quotient holds for solvable groups by hand, and it was like, I don't know, 3 or 4 pages of not really understandable things going on. And now with this, it's just like, okay, it's true for all groups with elementary, so all elementary amenable groups. And so you really get a lot more groups. Sadly, we don't get more corollaries for where we can actually apply it, because some of the the groups where we know FDC, namely the linear groups and elementary mutable ones, so for linear groups, I proved it that it holds by hand, and it was really sometimes a bit annoying to do that, but it worked out. And for elementary amenable ones, this condition actually says it has a finite Herschel length, and then we already know Farrell-Jones, so it doesn't give anything new there. But well, you still could hope that with all these properties you can come up with some new groups. And now this condition is like a lot easier to check than this one with the quotient. So that was somehow the motivation to get that. Yeah. Yeah, I don't think so. Yeah, I mean, so I still hope that you could do something to actually prove that it's close on an extension or something, but I wasn't able to do it, and it seems like really hard. So because otherwise you could use this to prove it for all elementary mutable ones, but I think and it also doesn't work to prove it for the unequivalent isomorphism and do something there, because there you don't really understand the right hand side where you now have not the grouping anymore, and then it behaves strangely. Yeah, and now one question would be, is regular FDC actually the same as FDC? So we don't know a counterexample. So maybe one of you can come up with one. So I don't know any counterexample that lies between FDC and regular FDC. Basically, because if you show FDC, you do it by starting with something with finite algebraic dimension and apply all the permanence properties, and then it will still have regular FDC. I don't know. I mean, I would say from metric space it's different, but for groups I don't know. But already for metric spaces you have to come up with something that's really complicated, so that you can't build your decompositions in like an ordered fashion, like in a regular fashion. But it still has to be easy enough to have FDC. So I don't know. Okay.